first ran into Peyton at VMworld last year. VMworld runs a mini networking conference inside of it called FutureNet, and VMware is hosting it, but it is still meant to be a vendor agnostic conference, this FutureNet, and they have people from all different parts of the industry, both vendors and practitioners, talking about what tend to be very provocative presentations that challenge the norm. And Peyton certainly gave a presentation about exactly that, a very disruptive sort of a talk about how to leverage open networking and really change the economics and shift power back to you as a end user and consumer of technology. Not an easy path to follow, the world that Peyton's in, but with that thinking in mind and that background where I first heard Peyton speak, and you can see that talk up on YouTube, by the way. There are people that shout and clap and applaud like you can't believe at the end of this video. I was probably one of them. I remember fist pumping. That's a thing I remember doing at the end of Peyton's talk. Anyway, Peyton, I'm building it up too big. Now there's a lot of pressure on you. I don't mean to do that. So
yeah, you don't leave much room for error. Thanks a lot, Ethan.
So Peyton, the problem that I set up for him to come up with a presentation for is, how do I build a network that delivers an elastic application? If you don't know what an elastic application is, Peyton's going to describe that. How do I build a network that delivers an elastic application while reducing the cost of the network infrastructure and services that support that app at the same time? So I threw a big challenge out there, and Peyton has some answers for us. So I'm gonna turn off my camera since Peyton's isn't up, and it would just be weird. And Peyton, off you go.
All right, cool. So as Ethan said, what we're talking about is being able to reduce your costs in your data center around building elastic capable compute or infrastructure. Now, what this usually how this usually happens is your company has been developing in AWS for a while, and then they get the bill, and then they're like, holy crap, how can we do this cheaper but still have the same capabilities as we do in AWS? And so, as a primer and disclaimer, what we're going to do is talk about how you could actually build infrastructure in your data center, how you can use things like white label switching and potentially even compute built by a company like Quanta that's an integrator versus using Dell or HP to allow you to deploy in that data center much more cost efficiently. I don't have numbers in the presentation, but I will be talking about numbers during my talk. But this is also just a primer. We're talking about some of the fundamental tools that you'll need to be able to make this happen in your data center. We're not going to talk about all the ways to get it done because there are so many ways you can cook this that it's ridiculous. And it really comes down to how does your company or your technical team like to deploy? How do they like to manage? Are they running CI/CD? So forth and so on. But as Ethan stated earlier, this is the business problem. Business is deploying an elastic application to their customers. This software application is their product, but they need to also be able to deploy it in their data center. They want to maintain a competitive advantage, be able to scale. They want to reduce the cost of the network infrastructure, and they would like to buy from anyone in the networking ecosystem. They don't want to be locked into a single networking supplier at all. This business needs to be able to coordinate workload demand with available network resources to ensure capacity and security, even in planned maintenances. Basically, they just asked you for an open source data center, meaning we can use any tool we want, we can put it inside the data center right away, and we can test it and develop against it in a very short amount of time and start seeing the effects of that testing and development very, very quickly in the environment in which we want to work.
So, I mean, well, you said basically the business asked you for that. I mean, that's your interpretation of how to solve that problem, that's what they asked for.
That's right. I mean, if a company comes in and says we want to reduce costs, what they're usually saying is, if I did this all in a vendor ecosystem, it would cost me, let's just say, $1 million. But we've only got about $200,000 to spend to do this. When you look at what it costs to actually run an open compute or an open source data center, you really are reducing the costs dramatically, and you are able to build things and scale them non-linearly. So it doesn't always just go up and to the right. You get a down curve at some point based on how much you're deploying, so forth and so on. You also, since you're developing the people that are actually running the network, you're getting to continually invest in yourself, which means your team gets much more capable over time. And that means when you see problems, the ability to iterate and ability to use automation or any other tool to fix that problem, you get to that solution much more quickly than you do when you're currently bringing in an outside party to fix those sorts of things. Does that make sense?
Yeah, no, you absolutely. I just wanted you to justify why you felt that was the answer. Yeah.
So we get down to the crux of it. What is elastic compute? So elastic compute is not this idea that your server can just sort of magically grow inside a data center. What it is a cloud computing concept that allows you to have multiple instances of a system or a service running across multiple pieces of compute, and then you have the ability to schedule each of those resources to be used at a certain time. So as I get a connection number one, it goes to the first server or first VM or first Docker container that's managing that process, and 2 and 3 and 4 would lace across all the other instances of that if that's the way you choose to do so. But it also develops a recovery plan, which means if server 1 dies or instance 1 dies, I'm able to take the things that it was doing and move it over to the other instances with very little recovery time. So the ability for them to continually inform each other of the status of what they're doing, but then also to be able to roll over. This creates an environment where we're actually able to fail fast and fail small.
So that's the hyperscale model. That's what they've been doing for a long time. Then it's all that philosophy of things are going to break. How do you engineer a solution that assumes infrastructure is going to break and be able to keep on rolling?
That's exactly right. And you lead me right into this next point, which is also, since we're moving what used to be very high functioning network processes away from specialized devices and moving them out to the edge, what I can do is I can fail small. So the idea that we have one big firewall for the whole data center, or even a high availability pair. Sorry guys, I'm dealing with allergies, so I apologize. If we have that and it goes down, the whole data center goes down. If I have firewall instances distributed across compute on my data center and one of those fails, it only impacts that portion. And if we have an elastic compute deployment, that means that instance goes down, but other instances can now accommodate for it. So it creates an environment where we're not putting all our eggs in one basket. And we also get to do a lot of things around efficiencies where we are actually able to handle more traffic, because what we're doing is we're sharing the load versus trying to funnel everything through one specific point in the network. Now we can do that on firewalls, we can do load balancers, we can do network access control with companies like Project Calicos, who I've chosen, and we can move common services like DNS, DHCP, and IPAM into compute via microservices as well. So basically what we're doing is we're saying we have a ton of servers in a data center. We have very little networking equipment in comparison, and we also have very many special functions on even smaller numbers of network devices like firewalls and load balancers. So let's distribute that against the compute, which we have a lot of and is easier to deploy, instead of trying to isolate that down to one logical box.
Now, okay, I just want to jump in here because this was a topic that we had earlier. Do you want to go back?
Yes, go for it. Yes.
So when I said earlier, if you could go back a slide, Peyton.
Mm-hmm.
When I said earlier today in the Ask Me Anything section in the 2 hours at the front, people were saying, how should I do firewalls? And this is what people are doing, is building firewalls in virtual machines, building load balancers in virtual machines, to replace this idea of the big hardware firewall. The hardware firewall is a 20-year-old idea. It's not the way that you're going to be doing it in a few years' time, because it's not possible to make those run reliably and stably. You only need them to be big. You only need hardware if you need a lot of performance. If you run a lot of small firewalls, you don't need one big one. You need lots of small ones.
And you also get to another point, which is you also just really trim down the failure domain. So in a big firewall, if you make a configuration error, you can blow the whole network off the map. If a programmer is using a firewall that's distributed against compute, he can only knock his product off. So it puts control back into the hands of the people that are actually providing a product, but it also allows them to recognize the ramifications of making those mistakes. So it's not a situation where, hey, Peyton, you're a network engineer, I told you to do this and it blew everything up. And I'm like, well, I don't even know what you're doing, but I did what you told me to. Now those producers of software actually have to see and understand what they're doing on the network via firewall.
And keep in mind that a firewall in a virtual machine, if you're going to use a commercial firewall, you can actually snapshot the VM, try to do the upgrade, and guess what happens if the upgrade doesn't work? You can roll it back.
That's right.
Just
Well,
go
and
back to the,
even better, you can actually run a sidecar on the firewall, which allows you to pull all this data out, but you could actually apply the new code to that sidecar and see how it happens, what happens to it first, because what it's doing is basically emulating everything that's happening in the first firewall. And if it dies, you just roll back the sidecar. You haven't even touched the firewall.
There's a whole bunch of ways to do it, but I think I was just going to focus on the ES concept for simplicity for those people who haven't glocked onto the idea that hardware firewalls are fundamentally end of life or end of design. You don't do them anymore. You shouldn't be. Yeah.
You shouldn't do them anymore as much as possible. I mean, I think that
right,
there might be
beyond firewalls, because Peyton, as you're pointing out, you're trying to move common services, everything that could be in a virtual machine running as a VNF, virtual network function on x86. That's where the world is headed. That's where things are going.
That's right, because you're the edge of your network has the most resources. Think about your router today. It comes with like a small amount of RAM. If you get a switch that's a layer 3 switch, you have to worry about the TCAM sizing and how many routes it can handle. I don't have any of those problems with hardware. Or excuse me, with servers. I can go get a server for cheaper than I can buy that switch that has 128 gigabyte of RAM and could run multiple versions of the internet route table if I wanted to. So also using it as a firewall, especially when we're only doing it for a very small slice of what's happening in our data center, makes complete sense.
And it's not like we're arguing that general purpose compute x86 Intel architecture and so on is like perfect for everything and just move it all. There's a reason that ASICs exist, right? The scale and performance and so on. But again, when you stand back and look at how you're going to architect this infrastructure we've been talking about, elastic compute, a lot of the features and functions that you would have normally thought of as a separate network appliance now gets absorbed as a virtualized function that runs on top of x86. So,
yeah,
all right, we've interrupted you a lot here. So
no problem. And these are all highlighted because they are actual links to pages that show you how to do this, whether it be from an open source methodology or not. One other thing that we should mention just before we move on is, yes, there might be a place for hardware firewalls in the near term at the edge of your network where you're making big global decisions or you're having to make a lot of denial decisions at the edge. But what you want to start doing as a network engineer and as a data center and infrastructure engineer is start making sure you're handling the global decision, but then making sure you're giving as much control to the people developing the product, because that allows them to be extremely agile and work. And again, it does come with the tagline that if they blow up their system, they blow up their system, but they will have recovery much quicker, much more effective than what we do when we actually blow the whole data center if the firewall were to roll over. So what does this mean for our networks? So basically what we're saying is we want networks to provide a lot of throughput. We want them to be able to be provisioned exactly the way that they should be. We want them to be able to move data left, right, up and down through our data center very, very quickly. And we need to be able to spin up compute and network services as quickly as possible in a repeatable fashion so that we're not worrying about human intervention. This means we want to get ourselves away from the CLI, especially when it comes to configuration, and we want to have the right tools that actually can allow us to add additional resources into our data center very, very quickly. So there's a lot that we just threw out there for people to chew on. Now let's start talking about nuts and bolts. How do we actually build this? Sounds really good. Well, basically what we need to do is we need to find a way that allows us to onboard networking and server equipment very, very quickly. And to do this, we've got a small tool set that we need to be able to implement. Number one, you need to implement a ZTP server if you want to, and a Pixie server, or you can also use a Maas server to do all the functions that we're about to talk about. You may want to have separation in the way your switches come up. Again, this is designed to be flexible, so you may need a ZTP server if you want to use Arista, Cisco, or Juniper. But if you want to use white label switches, you could use that same Pixie server or a Maas server to be able to load up your compute as it comes online and your network devices. You also need your general support systems. I'm about to show you Maas right now, but some of these systems, DHCP, DNS, they actually come with Maas, so you may not even have to actually deploy those individually as well. On top of that, we also chose Cumulus for our switchOS. We did this because we wanted to be able to deploy both white label switching or mainline switching. So if for some reason your VP comes to you and says, no, we have to continue to use the mainline switch provider that we've used always, but you want to have the ability to move from one switch to the next, you implement Cumulus to allow you to actually load those switches correctly, give you the same CLI, give you the same set of functions, and then be able to integrate white label switching later if you can. We implemented Calico for network access control, one, because it can run on bare metal and VM and works with Kubernetes, but it also uses BGP to program the vSwitch on the device. While we may not agree that BGP is a good routing protocol, I think it's personally terrible. It does allow us a very effective communication methodology back down to the servers that are in our data center, and it allows us to constrain communication between devices based on a set of rules that we put in place. So, and it also allows those rules to be dynamic. So if we turn up a new server or a new service, and we already know that that service needs connections to 3 or 4 main things in our data center, those can be pre-programmed right away and can be changed on the fly very quickly.
So just about BGP, Peyton, there's also several different flavors of it available in the open source world. Now you mentioned Cumulus. So
yep. That's
when we say BGP in the context of Cumulus, is that picking your own flavor and rolling it into Cumulus, or are they supplying their own BGP?
Cumulus, I believe, actually has its own version of BGP that will work fine for the implementation that we're talking about. We're not looking at doing a lot of routing information via BGP. We basically want the device to know where to send the next packet and if it can or cannot send that next packet. Meaning we just want to be able to implement the IP tables of the device, or via the hook that Calico puts into the server.
Got it. Yep.
Yep. And a quick preview of this. So if we look at Maas, the reason we picked it was because in the front here, you have, this is basically the dashboard that Maas gives you. It lets you look at all your devices as they're being deployed. This can be switches and this can be servers as well. But it also allows you to do hardware testing, chassis management, network management, and service tracking, so that you're actually looking at what's happening on your network, and you're able to run a battery of tests automatically, get the results, and see what you have to correct, or see if there's nothing to correct. It also comes in with built-in DHCP and DNS. The other reason that we're also doing this is because it's allowed to be clustered, which means you can go practice with Maas very, very easily, get a few servers, a few switches, but then you can actually scale that deployment out, and you can literally have regions of switches and servers deployed via Maas on top of stuff you're already doing today. And also the pricing is pretty cheap. So if we look at Maas, one of the things that is really nice is that you can start at free. So you can literally go start working on this, and then, or you could go get $5 a month per machine and spend $20 a month and have 4 machines running on Maas so that you can play with it. So it's a very easy way to sort of get into this environment without spending a lot of money, and you can get to the source code right away.
And Canonical's behind it, which is a name that many people know. It's not a fly-by-night, we did this in our garage open source project that gets abandoned in 3 years. There's an adult company behind the product.
That's right. And we chose Calico for the same reason. You're actually able to start to join the Calico project and be able to start deploying the service and practicing it in your data center for free, pretty much, as long as you register with them. You can pull it down through GitHub. And this is the solution that really makes Calico work for me, which is I can be inside a Linux kernel, I can be inside a VM, I can be on bare metal, but what I've got is a centralized database telling these devices what they can and can't talk to. So now I don't need anything like VXLAN. I don't need to worry about making sure they're all in the right NVGRE space or a VLAN. I literally just need IP connectivity into my data center, and then this actually informs the servers what they can and can't talk to. And that can be even to the open internet. It can actually say that you can only talk to certain services inside the data center and you're not reachable by the internet if you wanted to have a backend service. Given the fact that a majority of this stuff is free or very cheap, what you can actually do is you can actually build an initial setup that allows us to start playing with this. Basically, you need 4 servers or 3, depending on how you set up your control system, a core switch, and then 2 whitebox switches and the other 2 servers. This allows you to practice all the things we're going to talk about in a very discrete and small way, and then allows you to get ready to roll out much larger implementations of this. From a network topology perspective, this is how traffic would flow. Obviously, the servers would attach the labels above, or to the switches above them. But we do have a management out-of-band scenario, because a majority of the servers need to be kicked over on a Pixie interface or some sort of DRAC interface on a Dell server or even an Open Compute server. So we actually have those servers hooking back into an out-of-band network that allows them to connect directly to the services that will deploy that for them. So this is actually the boot sequence. So after you've got your Maas and an additional ZTP if you'd like it, and you've got DHCP and your CMDB set up, you're able to rack those switches, the switches and the servers both boot at the same time. The switches go and get their config via ZTP, Organo, or Maas. They can build Open Network Linux, and they can also put on Cumulus. And then they are completely configured to allow communication within the data center. Now remember, this is deploying a range of IP addresses to that switch that allows it to talk layer 3 both northbound and also down to the servers that are connected to it. That should be the limit to the config, other than probably some DHCP or Pixie relay stuff. But since the servers are doing Pixie via the out-of-band network, what they'll be able to do is they'll be able to load Calico and register with Kubernetes, they'll load Maas, which will then kick over to load Calico and Kubernetes, because you can chain things through Maas. And at that point, you should see in Maas all your switches and all your servers, but also in your Kubernetes and Calico instance, you should see them all registered as well. So you can now actually just start to deploy those servers right away to anybody that would want them. And you can manage it through Kubernetes on how much of your resources you're actually utilizing. And Maas also gives you a lot of tools around that too.
So for anybody that tuned out for a minute here, we're talking about standing up physical switch infrastructure quickly. Rack it, connect it to the out-of-band network, it phones home, and it gets sent a configuration. All the work's been done on the ZTP and Maas end to know what to send that switch, so that you can immediately begin plumbing hosts to it and have them pushing data.
That's right. And what it gets to is the point that you don't have to do a lot of the tasks you've had to do in the past to load things. These things start coming up automatically. What you're doing as an engineer is planning out how that data center scales and where things should be in the future, and also managing how it's being utilized in the present, so that you're getting the most benefit out of your data center resources.
Got it, yeah.
Another thing about this whole boot sequence should take less than 24 minutes. Why is that important? Because what we'll see here is you're actually able to put racks and racks of switches and servers in place, and each rack should take less than 24 minutes to register with your system. That's an amazing change in comparison to where we used to be. And we've done that because we can.
24, where did 24 come from? Just curious.
Yeah, so when we ran tests doing this at a company that I used to work at, 24 minutes was the time it took to actually load all the Maas instances onto about 42 servers, and also bring up the network instance on the switch and be able to verify. So it's really a majority of the time is actually verifying that the network and everything is all set up correctly. On top of that, since you have a single server doing your Maas, you're more than likely going to have some of the Pixie systems queued up as it starts relaying the Maas image. Now, the Maas image is very small. It can be less than 10 meg. It could be up to 50 meg. It all depends on all the things you want to do with it. But it should take less than 24 minutes for the whole thing to come up and verified. That means you've audited every network connection. You've audited every piece of RAM in every single server is set up correct or is working correctly. All the hard disks are registered correctly. All the CPUs are what you ordered, and that they're all connected to the larger network and can be utilized right away.
It's such a, I mean, anybody that has to deploy at scale has to deal with these tools of necessity. People that are used to throwing one switch out at a time because, oh, we got to stand up this closet. Oh, we need a little more capacity in this rack. You know, it's just a different ball game. But when you begin thinking about what it takes to make a network that can react to capacity needs this quickly, you all of a sudden have desperate need of these tools very quickly.
Yep. And again, what we're looking at doing is getting engineers to focus back in on how to plan for their networks and their capacity needs and manage the capacity they already have, versus having to continue to troubleshoot and deploy things that then get taken away by a group, then they have no insight. This actually provides a situation where we get a large amount of insight into how our network is being deployed and utilized, while at the same time giving a large amount of freedom to other groups to utilize that network. And that creates a very interesting ecosystem where you're able to move very fast. Now,
Yeah. Now, so one more question here regarding BGP. You chose it, and then Greg dumped on it, and you also dumped on it. And so maybe it's worth taking a minute just to, what's the big issue with BGP for those that are curious?
For me, BGP is if we look at BGP and the way it allows me to move networking traffic, it has had way too much responsibility and it's got way too few capabilities. And I'll quantify that by saying, if I look at the way BGP is defaulted with AS traffic information, it was designed with the idea that one AS would only connect to another AS at one location. If you extend to another or even another location, you have multiple peering points with both ASs, you lose a lot of your traffic control unless you have high coordination between both parties. Meaning, if party A has to tell party B where his traffic is coming from or expose internal network information, instead of being able to route via BGP the way you want. In other words, if I see a traffic come in entry point 1, I want it to go back out entry point 1 instead of going to entry point 3, because that's where the IP address of the loopback that's running my BGP is lower than the other, and therefore it's going to go out that way. Right. So, but if we constrain that into a data center, there's not many decisions BGP can make. So what I'm really using BGP for is just information to the server on what it can and can't talk to, and to give it its actual route path. But we're limiting to a very discrete fashion what can be done inside that data center.
Okay, fair enough. I didn't mean to derail you. I just felt that was a question worth.
So BGP, the big problem with BGP and with all routing protocols today, I'll take a 2-minute diatribe on this, is that they're all database lookups, and that they're all extremely inefficient for what a database lookup is. If you look at how network devices perform doing those database lookups and understanding where it has to forward a packet, we should be able to do that much more efficiently and have a wealth of tools around how we move and monitor and manage data traffic that we, if you look at the database lookups that happen inside multiple software packages over every single day, they're doing a lot more than what we're doing, but they have much more discrete control and tooling around that. Whereas us, we get some SNMP database updates, we get to look at routing tables, but that's about it. So it's not really efficient as it should be, and we stopped innovating on routing protocols in general about 10 to 15 years ago. Is that good enough?
Now, another question just flowed in about the larger network here that's being constructed. Are we assuming it's a leaf spine?
Yep.
Do you hang? Okay, if that's the case, then do you hang the Maas managed network off of the existing leaf spine, or is it part of the separate out-of-band network?
It would be part, so the Maas would more than likely be part of the separate out-of-band network, but you'd still have a sort of leaf spine connectivity matrix for that. One of the things that this presentation doesn't address is if your data center gets extremely large, and let's say you have 50 rows of compute, you may run into some issues where you have too many hops between specific applications that are looking for extremely low latency, or because of latency, it can't make decisions fast enough. At some point, when you get to that point, you will have to manage where individual things can spin up inside your data center so that they are constrained around a particular instance. But we're not talking about that today because we're only going to do about three racks.
Right.
When we do leaf spine, though, again, if we're looking at it from the overall perspective of how things connect, you do a small leaf spine for your out-of-band network, or you'd want to mimic that just because it's easy to run a couple of pieces of fiber exactly the way you're doing it for your actual front-end network. And that would also allow you to have efficiencies around how you move stuff as things boot up. The other thing that Maas provides, I think it shows here, is that you can actually get to a point where you have multiple failure domains. So you could have a primary high availability Maas instance and have a secondary, and you can even have regions of that. So within your data center, you could have multiple regions talking to multiple devices. So when things need to boot up and be utilized, you get a very efficient way of doing that. And it doesn't require much hardware either. Now, what have we achieved so far? So just based on the last 4 slides, we've been able to introduce new networking hardware in minutes, and you have a standard loadout that is auto-generated and a mechanism for reimaging those switches and those servers anytime you want. You can literally go into Maas, or you can go into Kubernetes and kick over those servers into a new instance if you want. You can actually verify and audit deployments as they come up instead of manually auditing it. This is where we've actually have a record that every single network interface works, and we tested it. That every piece of RAM, CPU, and hard drive works, and we tested it, so forth and so on. This means deployments happen much faster. All the things that we used to do in a very linear, manual fashion now happen in, again, less than 24 minutes based on my testing. And we can introduce new computing minutes, meaning the systems that in place to onboard large banks of compute anytime. And so I'm going to go to presentation mode to show you my cute little animation here. So basically that means that you can actually roll servers into your data center fully configured. If you go to Quanta, they can actually build you racks of servers with the switch of your choice. They could roll those into your data center, hook them up to the larger network, and as soon as they're powered on within 24 minutes, those servers are completely available for someone to utilize, and you haven't done anything to it except audit it and image it correctly. You've also done the work to provide IP address ranges and all the configuration that need to be available to the switches and to the servers ahead of time. So you're not worried now about building it on the fly. It all happens when it lands.
Yeah. What about physical cabling and verification of that?
So that's what Maas does. So the physical cabling will tell you that a server A is connected to port 1 and its backup is connected to port 24 on switch B. So you'll actually get a network map built out by that.
Okay, so if Maas is involved, is that actually LLDP or something else?
I think you can use LLDP. I think it's actually primarily LLDP. In fact, one of the cool things that you can actually do with that is as you use Maas and you're using LLDP as a way to bring up servers and switches, you could actually even start doing your configuration of the switches based on the port that they are on the main switch above them. So it's not that you have to know the serial number or base MAC address of the switch for it to get the right configuration. It's because it's off port 1/24 of the core switch, and port 1/24 gets this range of IPs, and 1/25 gets the next range, so forth and so on. That means that if that switch dies, the next switch that goes in its place and is plugged into that port gets the exact same configuration, and you don't have to worry about going in and changing out the base MAC or serial number.
Cool. Excellent.
Does this also have an impact to operational upgrades and updates? So when you go to update, do you just reboot it and deploy it as if it's a new switch?
Yeah, you can actually do that. So you can get to a point where you move the load, the virtual load that's on the switch, or excuse me, on the piece of compute, over to another one that you're not going to upgrade. You re-kick that server, make sure everything that has worked correctly. Actually, you'll probably re-kick the whole stack, and then you can move the load back if you want, or leave it where you put it. So actually, you hit the third point there, Greg. You can reimage both network and compute in minutes if you want.
So it stops being an upgrade and just becomes it becomes a deployment. You just redeploy it. Yeah, you don't actually. Yeah.
Continuous deploy, yeah. Any questions on this? We deploy network devices in minutes. This is what we talked about earlier. We now can do compute banks in minutes. I call them banks because there's a whole bunch of servers there. We can reimage. We can provide network access control. We can also provide layer 2 connectivity if we have to via either Docker Swarm or VXLAN or some other tool.
Backing up to Calico there in step 4. Calico, I'm trying to remember, is that an overlay solution or is that a BGP directing solution?
It's a BGP directing solution. It doesn't use any overlay connectivity at all. It is literally saying that your IP address, it updates the routing table of the server to say that it can talk to this thing or that thing and not the other thing.
And it's doing route manipulation to make that happen effectively.
It's actually using BGP to form the route tables on the server.
Yeah.
So if we look back at how Calico is deployed, The Felix kernel inside it is actually informing routing and IP tables within the Linux kernel or the Windows kernel inside the device you're deploying it to.
Oh, and IP tables. So there's
That's right.
also host-based firewalling that can be done there.
That's exactly right.
Yeah.
Conceptually, it's similar to NSX in that the IP tables in a Linux host is being manipulated to act as a vSwitch.
That's
So
exactly right.
tables,
The only difference I'd say is that the Calico is much cheaper to start deploying than NSX and allows you to start understanding how to actually deploy this stuff in your head and practicing it conceptually at a very low cost. And then once you have the fundamentals down, bringing in an NSX, you understand how that's going to orchestrate things to talk to each other.
That's right.
Versus having to pay for it up front.
So you're suggesting that Calico is a way of proof of concepting at low cost with limited capabilities, and then if you then go to buy a more expensive product, you'll understand what you're buying, and so that makes for smart buying decisions. You know how much to buy, what licenses to buy, why you're buying, instead of overpaying. Like if you go and talk to VMware, they'll have the full sales mechanism engaged to sell you the maximum amount of product, and you're not well equipped to decide quite what you want and what you don't want, and you end up, well, most customers end up overpaying for licensing. They buy features they don't want or need because the salesperson has to make budget this month.
That's right, and they don't even know how to say no. We look at, they said the salesperson tells you have to have this feature, and you're like, well, okay, because you don't know, you haven't played with it in a data center, and you don't really understand what you do or don't need. Calico allows you to understand the constraints and things you need. You may not need layer 2 at all from NSX, and you just need layer 3 routing. So don't pay for those licenses.
Yeah.
Calico deal with overlapping IP address space?
So Calico would allow you to deal with overlapping IP space. You'd have to have zones inside the Calico server. So if you had multiple 192s deployed, you could use it over and over again. It would understand the construct around that actual database for that network versus, this is my understanding the last time I deployed it, versus having to have a Calico instance for each individual one.
Got it.
The only weakness in Calico, from my point of view, is the use of BGP as a message bus or as a messaging protocol. It just doesn't seem to make sense. But in reality, it doesn't matter, because whether they use REST or JSON or gRPC or netconf, it doesn't really matter, because it's only between the controller and the Linux agent.
That's right. And I agree with you. We should all start participating in Project Calico and build a new routing protocol and get rid of BGP. But I'll let that for another day.
Plenty of efforts along those lines in the IETF right now. So
I'm telling you. Okay, so now what? So you've built this system. You can deploy lots of compute all at once, and you can deploy a whole bunch of servers. Bada bing, it's there. What do I do with it? Well, first off, you have to understand what being an elastic application means. It doesn't mean that there's some magic that allows it to just scale. There needs to be a system in place that manages that process, and applications be able to function in a distributed manner. We're not talking about putting your email server and making it elastic. That's probably impossible. What we're talking about is taking applications that are designed to run across multiple servers, allowing them to communicate and scale correctly. So let's take product one. Product one can't just live on rack one and server one. Product one has to be able to live in a dynamic location in a compute bank. So any server, it'll get logged inside your system, but any server inside the network. And then the elasticity allows you to also have things like load balancing distributed against other compute. So this is where you ingress the traffic on a server, and then you egress it back out to your network, and then finally to your product. Or you could load balance them amongst other devices. This is one of the key features that allows you to say, okay, if server one goes down, I can use the load balancing to move over to server two. Or if I need to drain the pool, does everybody understand what that concept is?
yeah, I assume that. I mean, and also, since there's a bunch of people twitching because they're thinking about statefulness and looking at your diagram and getting angry, address statefulness along the way here.
Right. So for your application to be stateful or be stateless, you actually have to give info. You can actually run both stateless and stateful applications in this manner. The amount of coordination between each server providing that specific function, it will dictate how much communication you have running between the other load balancers or products in your stack. Now, So for what you're actually doing at the load balancer level is you're greeting traffic that's already headed to a particular server that needs to understand what you're sending to an application. So that load balancer may actually be serving multiple products and maybe choosing to send it product 1, product 2, product 3. Since that load balancer instance is stateful because it's managing the state of a particular session, it needs to share across the other load balancers in its that is managing its application or that are working towards a set of applications so that it's doing it correctly. Whereas the product itself can be stateless if you want, depending on what we're talking about. And so it doesn't have to inform the other servers or other products inside its data set on what it's actually doing. It just does that application, i.e. a DNS lookup is a stateless application.
And again, for stateful, in this kind of a scenario, everybody that might get an inbound request needs to understand state of a given flow so that that doesn't fall over.
That's exactly correct. And it also allows you to, again, if you need to drain the pool, what Load Balancer 1 can do is move the application in product 1 in rack 1 over to rack 2, but it may want to inform Load Balancer 2 and 3 that it's doing that as well.
And again, this goes back to that application design. You can't just do this like with a mail server, as you said. You got to have an app that was designed to run in this manner. So there's a marrying here between developers and infrastructure people to know what the expectations are of the infrastructure, and that the application can take advantage of it.
That's exactly correct. You know, even if you want to build an application in an elastic capable data center, if the application itself isn't elastic and if you don't have the right tool chain involved, you're never going to be successful. You have to have the right, so part of this conversation is around being able to give yourself a lot of resources very quickly to reduce the costs of those resources, but it's also about investing in the way that your company is actually designing applications and understanding the tool set around it so that you're actually over time building out applications in a way that can be moved on-prem or off-prem or anywhere in the world that allows you to have access to the compute. In this situation, you really could have product 1 living not only in your data center, you could also have it live in AWS. And you could have additional resources outside your data center directing where that application gets serviced or where the requests to that application get serviced. That's a far cry from what we're talking about today, but those are things that you could do. This also means that we can do firewall services, much like we're doing load balancing, as we talked about earlier in the broadcast. And this also means if we move to a microservices model within the network, we can actually start distributing small things that people need that don't need to be in a massive server that's serving them all, like IPAM or DNS or anything else. We can distribute that through the data center and allow people access to those resources. NTP servers is another good example. You could literally spin up a microservice that is an NTP server for a specific service, so they're all coordinating off the same NTP server versus having to buy a specific device. Instead of buying an InfoBlocks device, you could actually be running microservices that perform all the function that an InfoBlocks is giving to you. The biggest thing that we have to understand as we're building this out is we need to be able to plan to fail. Meaning, again, we talked about devices are going to fail, or we're going to have to move things, or we're going to have to upgrade them. Devices have been failing in networks and in data centers for years. The difference is that the new theory on building into a data center is that you recognize there's going to be a failure, you plan to fail small and to fail fast. So if the IPAM in the first rack dies, there should be a way for us to roll over to the IPAM in rack 2, or you should have a system that recognizes that IPAM failed, pull as much state as it can and move it into another instance that it spins up on its own, versus once that IPAM die, you have to go and do some sort of large recovery sequence.
Now, Peyton, the way you've laid this out, it looks like you've done this in production or some flavor of this. So a question that comes in from the audience, what issues have you run into with this design?
So the biggest issues that I've run into is overthinking orchestration, and therefore bringing in a vendor that ruined our deployment. So if you don't have the right team, you're usually going to use that, or you don't have the right technical talent on your team to make this stuff happen, you're usually going to run into a vendor ecosystem. I would highly leverage don't do that, or highly request you don't do that. I think that if your team did the research and figured out how to understand orchestration and looked at the tool sets that are available for it, you'd be actually much more successful on your own. When we did this at one company, we had a vendor come in. A team of 8 was initially on the project to make this thing work, and over 2 years and 120 more people, we still hadn't gotten it working the way they want, because of the fact that we were trying to take what the vendor built and apply it to ourselves. And there were all these edge cases where it didn't work quite right. So we had a lot of orchestration problems. We had a lot of things that were falling over. We kept trying to accommodate for what the vendor was providing for us, instead of going out and using open source tools that we could edit on our own and make customizable for ourselves. I had one of the engineers that was on that team leave and go to Hulu. He's actually written a blog post about this called Donkey. Hulu has a system that does all the things that we're talking about now as a platform as a service, so it actually goes one level higher. It took them 3 months to build that, and they've been using it for the last 2 years. So they took a very open source perspective to that, to go and figure it out, meaning allowing the engineers to take the time, allowing the engineers to practice with the system to make it work. That's why when we started this, I wanted everyone to start looking at it from a very small perspective. Let's just take a few servers and start understanding orchestration and network deployment and verification that way, versus jumping straight to the end. So when we're here, we are at the end of a very long journey where we've been figuring out this stuff for ourselves, versus just jumping into this day one. So what does this mean? This means that networking and infrastructure engineers get much more efficient at menial tasks, and they get to start transitioning services to compute, and those systems can come online faster and be more robust. This also means that the same engineers can be informing security decisions and implementing global security postures without being involved in every infrastructure need. It makes us more scalable, impactful, and eliminates the needs for tedious tasks, and turns our time and attention back to large-scale engineering.
Okay, so let me play devil's advocate here. It sounds like when everything's working great, everything's coming online, everything's getting stood up like it should, that slide is all true. But there's got to be a skill set involved in something ain't working, and you got to spend some amount of time dealing with whatever the tools that you've customized to work in your environment that went sideways today, etc. The new pod did not come online, and everyone's losing their minds because we need capacity now, and something went wrong. So there's got to be that aspect of things as well.
Yeah, I mean, you'll need to have a tool set that's one of the main things that you have to do when you do this is build out a tool set that allows you to understand how your compute is functioning, how your network is functioning, how it should be functioning, and be able to baseline that in comparison to what's actually happening at the moment. If you're expecting to be running at 50% capacity of compute, just throwing out basic numbers here, but you all of a sudden are running at 10, that's an immediate warning that something's going wrong. You need to be able to understand health of all these services as they're running as well. If we saw a decrease of 80% in the traffic in our network, or transactions in our network, we would want to figure out and make sure immediately that it wasn't something that was happening in the network, or some tool was failing. But a big part of this is CI/CD, so continue integration, continue development, or deploy, which is you should be constantly practicing with your own infrastructure for failure or for continuous deployment in a way that allows you to continually verify that those processes are working, allowing you to scale multiple IP addresses, add additional compute as you want, but you're always testing the system that does that, instead of saying, I know the system is just going to work, and sort of leaving it in Schrodinger's box.
You're saying don't just test when you're making a change to the system, but you're testing constantly, like you would with any monitoring system, to validate that the processes you rely on are always working and functional.
Yeah, and but there's a different twist to it. So if we look at the way that we've been managing and monitoring networks for a long time, it's usually asking the network how it performs. Things like Thousand Eyes allow us to actually look at how the network is performing versus what it tells us it's doing. And if you have a tool set in there that's not only checking the health of your network, but also the health of the services running on top of that network, you get a much more complete picture of how things are going to are operating, and you can actually start to model out how things scale. So you can actually start saying, yeah, once we get to 84 racks, we're going to have to look at a different architecture, or we're going to have to split this into regions, whatever that thing is. But that gives you a tool set to actually do it, versus what we currently do right now is we actually build this stuff in sort of a very discrete fashion. It's all sort of it's not mass applied, so we don't get the benefit of all that tool set, and we're actually managing things very, very manually. Every time I deploy a new rack, it's a new adventure.
I like to call it artisanal.
It's artisanal, yeah.
Handcrafted. Each piece is unique. Every deployment is unique, with love and
yeah. It's like growing babies or growing cows or something like that. The one thing that you also get is, let's say there's a change that needs to happen, and you figure this out when you're building a rack. You're able to actually go apply that change to all the racks in minutes, or stage that out over a couple of days, whatever you want to do through your tool set. Whereas today you have to actually log in or run sort of scripting system that makes a change to all those switches or servers or whatever over time. And you have to do that very manually. The tool set's not there for you to actually pull out statistics on what failed. You usually have to go and look at like a failure log. But by doing it over and over again and actually having a tool set that you've tested, you can have much more confidence in the fact that you're going to roll out a change. It's not going to knock any services off. And that means that you can move on to the next thing that you have to solve, or the next thing that you want to build.
Monitoring or analytics, most likely.
Yep.
Now, someone observed here and sent through as a question, really a comment, that build it yourself seems to be the most common advice I hear when researching automation and orchestration. And I hear that too, but I always stop and wonder at that, because every IT shop I've been in has been understaffed. And when you want to put the time and investment into tooling or any sort of a process to make your life better, it is enormously stressful just to find the time to sit and research and develop and test, and then finally put that new thing into production. If you can get a quick win, that's one thing, but trying to build it yourself seems really hard. So Peyton, when you've had success here, is it because the business you were working with was on your side and there were additional bodies thrown at this problem too? Because this is really a different way of doing IT for a lot of shops.
Oh yeah, totally. It's a much different way of doing IT. The thing that you have to understand is when you go to your go back to your business and you start talking about doing this, the other thing you need to have done some research into the cost of white label switching in comparison to mainline vendor switching, and also easily available compute, or someone like a Quanta, an integrator, versus continuing to buy from Dell and from HP. What you're going to be able to show there is anywhere from a 25 to 50% reduction in cost across the board. And what that means is
talking about acquisition cost.
Acquisition cost from a CapEx perspective, right?
Yeah. And
what that means is that you can talk to them about methods of scale that you couldn't in the past, and meaning, and due to those cost savings, you can also say, hey, what we can also do is we can actually provide a much larger suite of services and much more robust deployment if you allow us to bring on a team that can go do this, or allow our team to go investigate and figure out how to do this. So it is a conversation that you have to have with the business as you're doing it. But in this scenario, the business has already told us they want to. One of the things that you're going to see happen for a majority of businesses is once they start understanding their Amazon bill, they're going to want to do this anyway. Some people estimate that AWS is 6 times more expensive than on-prem compute. We can even make it that number lower if you're doing the open source model that I've described here. But
did you just say 6 times more expensive if you throw all your compute up at AWS?
Oh yeah, over time it's much more expensive, especially when you get times when you have to scale up. Those S3 buckets are so expensive over time, and you're sitting there looking at storage that you're renting every single month. It gets so expensive. It's ridiculous. And the other problem is that most companies that deploy in AWS don't have a tool set that allows them to understand what they're spending. They don't have an application registry. They don't look at how many servers they have deployed. Someone logs onto a web page and just orders and starts doing their thing, and nobody audits that stuff. Another thing that you can do inside this data center is actually build out an application registry, because you see where everything's being deployed, and extend that function into AWS, so you can actually start to talk about, but the business can start to understand how are we spending so much money, and which is the better place to start deploying services. you've seen companies like Dropbox say that they're going to save $75 million a year by actually doing on-prem compute. Now, they're a very large company, but I can think of wealth of applications where it's actually cheaper to do on-prem compute than it is to do it in AWS, simply because if you do it in the way that I described, you're going to have more than enough resources available to your company, which is the number one reason why they're going to AWS in the first place. And those resources are reachable instantaneously, much like when they're at AWS as well. So you're actually going to get the same sort of service model that AWS is providing to your business in your own data center. And that's going to make you much more attractive. And over time, again, we do have to run some models there. Over time, the company will understand how much cheaper it is.
Can you roll ahead to that slide, that next slide there? Because there was one more point I wanted to raise. Okay, you meant that second paragraph. You say engineers can be informing security decisions in implementing global security postures. Would you expand on that idea?
Yeah. So if you look at what the engineers are doing inside their application, they can actually be making security decisions, whether to have a port open, whether to accept a certain kind of request across their application worldwide. And what you've given them is the freedom to do that and be able to fail. So they can go and fail, and it just takes down their application. It doesn't impact the larger portion of the network, and then they can go and fix it later if they have to and bring the service back up. But that means that you're not involved in every single decision around security in the network. If we get back to the big bad firewalls at the front of the data center, every time something had to be configured on those firewalls, it meant a network engineer had to review the change, had to talk with the system engineers and why they needed it, and they had to go and make sure that they weren't going to mess up something on another service because it was controlled at the firewalls right there, managing things for everyone. What you do at the firewall or at the edge of the data center is you provide a set of global rules that says we're not ever going to let this happen, we're not ever going to let that happen, but anything else other than those things, you can do what you want. So that means the same engineers that are working on that infrastructure or working on that service can be informing security decisions and implementing global security postures for that service. And you can be implementing global security postures holistically that everybody's agreed to without you ever having to be involved in what they're doing.
Well, I think I've drug you through your entire presentation one way or another. Are there any other closing points that you wanted to make, Peyton?
No, I think that one of the things that most that is I'm trying to communicate the most in this is let's just go out and try it. Literally find 4 servers, a few whitebox switches or whatever switches you want. Go get the applications that we talked about in the presentation and just start playing around with it. You know, I've seen engineers in 3 weeks figure out how to make this stuff work and start throwing in much larger server sets inside our labs and actually start showing we could do it at scale in a very quick amount of time. A lot of the things that we described in here, Cumulus and Maas, Cumulus allows the network engineers to have a very similar feel to what they're used to inside the switches because of the CLI that's enabled, but it also gives you all the functionality of the of Open Network Linux and more. And then Maas allows you to actually see things happening right away. You get to see servers registered, you get to see when they go down, you get to audit those servers, you can play with pulling network interfaces out, and it all allows you to learn very, very quickly. That's the number one thing I'd say is just go give it a shot for very little CapEx costs up front, or just find some spare servers and switches and give it a shot. And I think once you start to see the power of these tools, you'll start to be able to recognize how impactful it can be to business.